Okay, so from the stuff that you did yesterday, just to kind of get that as a idea of how well it went for the stuff that I kind of sent you home with, how did that sort of go?
Good. No, it was all right. I think uh, everything went relatively smoothly. I think the only challenge for me is that times I would struggle understanding why we're inputting a particular code, uh, why we have to do it that particular way, or what it means. So it got to a point where when I was about to do the practical, I redid everything. So when I was getting to the first practical, I found myself asking, the way that some of these questions are being phrased, would I be able to understand it if they were phrased just a little bit differently, you know? Just to show that I don't think I grasped the whole idea or the concept behind some of the things that we were doing. So that for me was a bit unsettling for me, just personally, because I feel like if I don't understand it, then I'm gonna have a hard time grasping the concept.
It might have been also the way I created the questions as well, or how I set it up, because the way we weren't supposed to be so rushed yesterday. So whenever we're doing the work, it'd be more like I'm sort of going along with you with it. So I feel like I can be vague because basically I could clarify if I need to. So that's why if I was really, and it's also because I'm trying to condense it onto one slide. If I was actually trying to give all the information, give all the clarity, I would really need to do it like two slides to give all the information, then ask the questions. So it's probably more on my side, on some of the clarity side. When it comes to the functions themselves, like I said, there's so many different ways to actually put some of these things in. And even the person I usually do the class with on this, we have different styles, but the whole product at the end really is very similar. So it's what we feel comfortable with. But one of the things that I was going to show you this morning, along with that, just to verify, so the rest of the code seemed to work fine. There wasn't, because remember, I was having the conflict package issues. Because I load more packages than you do, it might be the fact that you wouldn't have that same problem that I had. It's just that I have a set of packages that I always load. And there's only probably 4 or 5 that are actually needed for that practical. Okay. So the biggest thing that I was trying to make sure of is anything that comes with, presenting your results. Because, like I said, this is what I notice is people have the most trouble with because they spend so much time on it. That's why I try to, show them, there are packages that sort of take care of this for you. So when it came to the tables and everything, you were okay with that? It sort of built fine for your work, because a lot of you are PhDs. So that's why I was trying to make sure that that's working fine. If it comes to the visualization, so any of these things that I actually did with this particular coding, the one thing I was sort of holding off from yesterday, or trying to, not, discuss it too much, was ways of actually finding help with these things. Because, like I said, there's help on these things, but you have to know sort of the basics before you kind of take it and start asking for help from these particular sources. So one of those was, the Chat GPT stuff. This with R works very well. Okay. So one of the functions like you were using yesterday was that stargazer. And you might not know exactly why you're using it. Hold on, let me find it. But you can take a particular code if there's something that you're looking for. So let me copy it. Okay, let me just grab it from my code real quick. So I'm just driving this from my code, so it's nothing it's particular to what we've been doing. But I could ask it to basically to try to get some information, especially when it comes to maybe improving the code. But this is one of the ways that you can get help from it. But it's not always just a guaranteed, this is the answer, the problem. A lot of times it gives you an answer because it's supposed to give you an answer. It doesn't say, I'm not sure. So that's why you have to be careful what happens. A lot of times it can help with cleaning code. It can help with understanding why you're reading a paper and they might even provide code and you just don't understand what that step was. That's where this can actually try to help you. It's not going to be perfect on a lot of things, but at the same time, once you start to understand this, it doesn't have to be perfect because some of the basics that allow you to understand what it was trying to do. Okay? So, you could use it for understanding anybody's code. It works well with R, not so much with Stata. It's not exactly a similar language. It understands a lot of it, but it also gives you functions that it doesn't understand in Stata. R is typically better, but I was trying to show an example where I just basically asked it, given some information, could you create code that showed a particular type of plot? In this case, a scatter that also tried to then create a nonlinear fit to those points. So this is sort of where this becomes a little bit helpful for you, especially when you're starting to learn this stuff. Even if you're using another program, you can actually ask it, can you translate this into another type program, MATLAB or something else? So that's where it actually becomes very helpful for that. But again, you can't just go and take something off the shelf that you don't understand to ask it and then take it as the answer. Okay, so I just want to make sure that you can use this, and I'm basically using just what you would get with the free version, which I believe is still 4.0 or 4 little o, whatever it is. So just ask, did any of y'all use something like this to sort of help you with the understanding of sort of the practicals and things like that? Because it's one of those additional tools that you can use. Yeah. Then I mean, in this case, I just asked it for a quick example of that, and then I asked another one how to make it interactive. Went through the same thing, and then it allowed me to go do this. I saw no trouble with it, so it should work, but I would actually have to run it to test it. Okay. So that's the one thing. The other was the last part of that practical, which was just sort of running through an example of Markdown. Were you able to actually create the HTML file that actually allowed you to create something that was similar to what you would find on a web page? Did it work? It didn't? Oh, okay. So I can try to, if you're interested in it, I can try to help you with it. That's why I was wanting to sort of do it in class, because there are little things that pop up that are problematic. Because I have a lot of the packages and a lot of things already loaded in the background, sometimes I forget that there might be a step that was something needed to be added. So if you are interested in that, if you let me know at the break, I can sort of try to see where the error is coming on, because like I said, I just forget, because I loaded all these things 2 or 3 years ago. So, once you get successful with it, sometimes you just forget it as long as it's working. Okay, so just let me know. We can try to help. It's very good for creating web pages, for creating summary type things that you need for your supervisor. Or even if you're working in the private sector, trying to coordinate with a team, it allows for a quick summary of what you're doing. That's not a final product, and then you can basically modify it as you go. Okay, but we can kind of go back through it once we start again, or once I know what sort of the issues you were having with it. Okay. Other than that, were there any other questions from the stuff from yesterday? Yes.
Um, okay, I wanted to know when we use the select, is it a function? Is it select function?
It's a part of
Select.
the duplar package, yeah.
Okay. Why do we put it in single quotations when we filter, and then at other times, like when we're selecting a column, why sometimes we put it in single quotation marks, and then sometimes we just put the name of a column as is without any quotation marks?
It's bad notation on my part sometimes. It's probably out of habit. So some of these notes are just, we've updated the examples, we've gone through, but some of the stuff has stayed the same from previous times. So sometimes we become a little bit more proper on how we're handling it because of how it gets fed into the next function. Sometimes there's a very specific way it needs to be pushed into the next function. So sometimes, as long as it doesn't give me a headache, I just forget about it. But you really should properly define each of the variables, quotation. Even sometimes I have to go away from that and actually put it as a combined C on the outside to combine it because the next function requires it that way. So it's probably more likely bad notation on my part. If you can show me the specifics, I can see what the next function is going into and see why I might not have needed to do that. Is there any other questions? Yes.
Yeah, what's the difference between a require and library?
To tell you the truth, I ever really worried about the difference too much. I'd have to actually look. I just know that if it's sometimes if I need to do the require, I do it. Sometimes the library, I do it. In my mind, it seems like the same thing. But if you talk to somebody who's computer science, they're going to tell you there's some particular differences between them. So I would probably need to look it up. I need to look it up myself to know. Like again, like that comic is not trained in data science. It's stuff I picked up over the years, and basically because wherever I picked it up, it said it. That's sort of what I did, and it became more of a habit than what I should have done. Okay, but that actually might be where we could actually get some information from this, because that's a good question. I never even thought about it. This isn't my usual typing keyboard. Oh, of course, is a good question. Basically, it's used to load primary function loading. Okay, so basically, you're going to get the primary function of all within the package. So that might mean that it might override a few of the problem I have with some of my like select and things like that, where I have to actually put the duplar at the beginning. It might be overriding some of that. Okay, so the require basically loads the package but returns true if successful and false if not. I'll have to find out more information. That doesn't really make sense to me, but basically, like I said, it's just probably bad coding on my side, or just bad habits I picked up as I was trying to teach myself. Okay. Any other questions? Okay. Okay, so that was the last portion of this. I did provide the code. Seems like nobody had trouble with it. I tried to remove anything that might have caused problems in terms of the fact that I load a lot of packages. But hopefully, if there is anything that you're not wanting to speak now about it, you can just ask me at the break. Okay. Okay, so today we're going to talk about actual regression instead of just codes. Okay. Now we have to go back through some of the OLS just to get a background on what we're doing. And because in the past, when we've actually done this class, we've noticed that there are some issues with sort of interpretations, especially for a certain class of models. So we're going to kind of go into those when we start talking about the categorical variables, just to make sure that we have a clear understanding of what is going on with those types of models and how we interpret them. Because it's rare that we actually have only continuous values within our models most of the time. Well, at least for the class of types of models that I use, as well as some other people use in the department. Mainly because a lot of times we can't get something that is in some way a measure or continuous measure of what our unit of analysis is sort of, something that is a determinant for them. A lot of times we can only see characteristics. This is what we typically do in development because basically we can see race, ethnicity, gender, types of governments. All these things are more like characteristics that we can see, but we don't have a really good continuous measure of them. So that's why a lot of times we'll focus on the categorical, but it's about interpretations of those variables. So we've just seen a lot of work where there's not exactly the right interpretation that they're using. So we're going to kind of go through those. And then we're to go through, the beginning in terms of OLS, so that kind of leads into those categorical. And then we're also going to we're going to go through heteroscedasticity a little bit, only because, this is seen some ways, most people, if you covered it in any class, basically they just say, run robust, that's it, and you're fine. I'll tell you that a lot of researchers, actually, that's just what they do. It's not always exactly right to do it that way. The reason why is because the types of groupings or how the situation is causing the heteroscedasticity or the clustering or any of those is not really always handled by robust standard errors. If you know for particular that you have clustering, you shouldn't really be using the robust, you should be using clustered standard errors because there is some type of form of grouping. So even though most people will just overlook it and say it's not anything that we need to worry about, really we should, if we want to get the proper inference that we're actually looking for in our models. And also, this is a better time to look at this than when we start looking at nonlinear models. In nonlinear models, it gets really more hectic because heteroscedasticity in the OLS models or linear models we think of as being just a problem with noise or efficiency. It's not a big issue when it comes to what we consider being unbiased or consistent. In nonlinear models, we do need to consider it because basically it does cause further issues, and one of those is bias or not being consistent. So it's better to sort of know the procedures that we might use to kind of do that, and it's better to look at them in the linear world first, and then if you plan on using it for the nonlinear, you can use similar type structures. And then I was going to talk about some other adjustments that we can use in place of the standard type modeling for generalized least squares. We're going to talk about the independent variable interpretation for interactions. I've sort of already mentioned that. And then I'm going to give we'll call it a brief look at quantiles. The reason why I want to look at these is primarily because this research is, for lack of a better word, is sort of exploding over the last 10 years. Ways of dealing with censored truncations, dealing with unobserved heterogeneity. And the thing is that when you run these types of models, because the objective function is not differentiable, we can't really use the same types of methods that we talk about when we talk about fixed effects on Thursday. So we're just going to get a brief look at how we think about quantiles, and then we'll kind of show a few things on the panel version of these on Thursday. But it just gives us a brief overlook of it so that we prepare for the next time. And also, if you're going to use them, you should really understand the interpretations of them. It's not the same, well, it is the same sort of as OLS, but with being very particular about how you speak about it. Okay, so there's a few things that it's basically just trying to be more careful as we go through these standard type modeling structures. So just starting out, a lot of times we just want to kind of go back through some of what we're thinking about. So just thinking about the law of iterated expectation. So basically, we associate this with probability statistics, and basically it's a good concept, or very helpful concept for a lot of things we do. Basically states that the unconditional expectation of a random variable can be expressed as the expectation of the conditional expectation given another variable. Basically, it's saying that the expected value of y should be equal to the expectation of y given some x. Okay, and in this way, we can basically look at, or I probably should say the next part. The weighted is basically the weighted average of the conditional averages is equivalent to the unconditional average. In this way, we can basically kind of push our outcomes and thinking about going from the unconditional to the conditional. Or sorry, the conditional onto the unconditional. In this case, we can think about, we want to calculate the expected, say, air quality, AQI. The only reason I thought about this is because a few days when I wanted to go for a run, for some reason my app was telling me that it was in the red. Basically, the air quality in my area was terrible. I don't know if it was a broken sensor or not, but it's like dangerous for everyone. But basically from this we can look at the region, and basically if we only have data on the pollution levels and by different types, by say industry, we can kind of give an idea of what we would expect to come out of this. So given the law of iterated expectations allows us to compute the overall expected air quality, conditional expectations of the AQ given the industry. So we kind of weight what goes into from each of the industries with the expected outcome of the AQI in this case. So all we're doing is just weighting everything. We know how much is coming out of each of the industries. We basically can weight them to get an expected outcome. Okay? So this is very simple. This is most likely not correct, but I'm just using the numbers to help out with this. We have different regions, and we have different types in terms of the industry types and pollution levels. We can basically, from this table, find out the expected value, or the expected pollution is 70. Whenever we take it as the pollution coming from the manufacturing is 85, the pollution coming from agriculture is 55. Using this, in this case I've made it 50-50 just to simplify everything. We get our expected outcome with respect to pollution given the industry. In this case, although we considered the variables in the zone, I considered them continuous. Sorry, I should have said that as well instead of being discrete. Basically, this also applies to how we sort of think about discrete variables. Okay, so just keep that in mind in how we're actually going about thinking about our outcomes that come out of our regression of results in this case. after taking that into account, the law of iterated expectation will move into OLS. So most of you have seen this. You've worked with it. Unless you're working with descriptive data, most of you know the background in terms of the OLS. Okay, so in this case, even though most of you might disregard OLS, see it as something that, is not really required for your research. A lot of times when we actually start any type of project, OLS in some ways is still like a baseline. It's a starting point. It shouldn't just be neglected just because, it seems too simple, the assumptions most likely don't work, all those things. It still, in some ways, should be looked at, okay? And I'm even saying this if I knew that your left-hand side variable was binary, okay? We call that an LPM model, or a linear probability model, which there's a lot of fault in trying to use that type of model or in terms of the probability way of using that model, but again, it works as a nice baseline, okay? So even though you're looking at the slide thinking we're going to talk about OLS, it's still useful in some areas, especially for the baseline. So just don't, throw it away just because you see OLS and people say that assumptions are going to be irrelevant, or, your assumptions kind of don't work well with it. So it's a nice starting point. Okay. So just to give you a refresher on this, so we're trying to estimate the relationship between two random variables, in this case xi and yi, that have some number of observations in, and we're considering a very basic model. Okay. In this case, notice that I've sort of not included the error term here for now. Okay. Just for simplicity. So we've tried to find the best fit line by minimizing the difference between the observed and the predicted. So when we're going through this, that's going to be sort of the key for, how good or bad we sort of did. We're going to be comparing the outcome between what we actually observe and how we actually predict the outcome. So sort of important here is these residuals, which is the difference between the observed and our predicted. And then whenever we actually we could write it out in this format as well. Okay, so we're basically we're looking at measures the variation of yi that is not explained, I should say explicitly, explained by x of I. And as we get smaller and smaller residuals, that usually means better and better fits, okay? And we typically are going back and forth beyond, trying to find variables that are actually improving our overall fit, but not trying to overfit in some cases. In that way, basically, because as we're doing better and better fits in this case, we're also adding most likely more and more correlation between your right-hand side variables and things that fall into this residual. So just remember that even though I've only explained it this way, we're thinking about this as anything that's not explicitly controlled for in the model, okay? And given the world, there's a lot of things that fall into it, okay? There's a lot of things that there's no way that we can practically measure them. So that ends up in, the unexplained in that error term. That's problematic for some things, and we'll get to that later in terms of endogeneity. But for now, we're going to assume that everything that we actually are controlling for, we're controlling for everything that's proper. So we're going to allow that error term for now to be, the expectation of it to be 0. Okay. In terms of this, thinking about that residual as well, thinking, why it's there is basically because we're dealing with observational data. Basically, observational data is noisy. If I did a quick survey around the room and I start asking you about things about work, your income, education, personal stuff, I doubt a lot of you are going to be very absolutely 100% truthful at all that, right? Who wants your personal information out there? That means usually you have to work with data that's not going to be 100% accurate, either because we can't observe it properly, we don't feel right asking that particular question, or just a number of different things. But the problem is that means that it's not going to be accurate, or it's going to be as accurate as it can be, but there's going to be some, difference in, the true outcome versus what you're actually giving me. Okay, so that means it's noisy. And that's what we're kind of dealing with here. We're basically capturing that unobserved factors affecting Y. For now, we're going to assume that it's not affecting X in the sense that they're correlated, but that's basically what's happening here. Basically, there's a true model that in some ways is apparent to us, but we can't accurately model it. That's why we do the best we can. Okay? Okay, so the objective function you've probably seen before, but basically we're going with the mean squared errors, or minimizing the mean squared error. Basically for reasons for doing this. The residuals can be positive or negative, and basically by squaring it, we know that we get rid of any negatives. Okay? We just want the absolute difference. Or in this case, the absolute squared difference, but basically we want it to always be positive, so we just get the distance, the difference between the actual and the residuals. Okay? This does have a little bit of an issue where it amplifies the impact of larger errors. So basically we become a little bit more sensitive to outliers. Okay? So this is a lot of times why well, I would say not just we, but everyone really, logs certain types of data. Okay? When you're looking at GDPs, you are on a huge spectrum. Okay? That basically has something that goes up for the most part and then has a long right tail. So in some ways that sort of is causing a little bit of a skewness in what we actually get. The problem is with OLS is that basically they're a little sensitive to these outliers. Now, the only reason I'm bringing this up is because a lot of times there's this whole literature that you find that basically people are hunting for outliers. We have an alternative that we're going to look at a little bit later, which is the absolute deviation. In this case, this is where quantile models fall in. So a lot of times when we're thinking about linear, or sometimes we call them the conditional mean type models, when we're looking at the conditional mean, we're looking at the entire conditional distribution, and we're looking at the average within that set. So you can think of it as the average individual, the average country, whatever your unit is. And from this, it's more of a global measure, okay? But we can also think about looking at the absolute deviation. In that case, we're looking at more of a local measures based on local properties. And in those cases, when we look at those type models across different quantiles, we can actually see the local properties, which means they're less influenced by any outliers, because they're based on the local properties. It's also a way of thinking about how we think about heteroscedasticity within our models as well. There's a whole way of thinking about it, but we'll kind of get into, I'll try to get to that intuition for when we start doing the quantile models later on. Okay. In this case, we have the coefficient on the xi, in this case, is basically equal to the covariance of x and y over the variance of x, and we're just adding sample properties of these by dividing it through by n. Most of you are familiar with that. When it comes to the constant, basically we're looking at the mean of y minus the coefficient on beta 1 times the x bar, or the mean of x. So again, this is just trying to refresh you a little bit on OLS. The primary goal of any type of estimation is inference. We're talking about results that there is sort of a bias towards significant results. Okay, so a lot of times when we're trying to, go through our research and everything, we love the significance, but again, we sort of focus on it being so much that we forget about magnitudes, signs, and other things on those coefficients. Remember that it's not about a high R squared or a decent R squared by itself. That helps. That means everybody loves that. R squares being high, they love that. Okay, but if the interpretation in terms of magnitude do not make sense, signs do not make sense, that's problematic. Okay, but there's also the going back the other way, that basically we do the model as best we can, but at the same time, the end result is we can't say anything meaningful about it because it's not significant. It's always a balance going back and forth between those two things. Okay. Sometimes we win and get both. Sometimes we do not. Okay. We'll talk about a little bit in terms of inference, of trying to see how we might be able to adjust if we assume there might be some bias in those standard errors, if we can make some adjustments to see if it's some type of, those adjustments actually help us say something meaningful about the inference. Okay, so a lot of times I'm going to try to be good on my notation. That's not always successful. But when we're talking about the population, I'm going to usually, or I should, most time not have any types of hats on these. Okay, what I mean by that is basically when I talk about the true or population model, I'm going to try to write it out in this format to where there's no hats. In this case, it's just trying to be notationally correct. When we have the hats, we're talking about the estimated model. Okay. U here is basically looking at the true error term. And there's a few assumptions, but a lot of the ones that we typically look at are linear relationships between X and Y. Random sampling, which I'm not going to say never happens, but we hope most time that it's random. In this case, challenges, there's a few other challenges we'll talk about in terms of strict isogeneity in a minute. And basically no perfect no perfect multilinearity. Basically, it means that we have to have some difference between the right-hand side variables. They can't be perfectly matching each other, a one-for-one type outcome. Okay? But the whole point is to isolate this impact of X, hopefully the variable of interest, on Y, amid everything else that influences this factor. The noise, everything that we can't control for, is basically going into the error term, which is sometimes problematic, mainly because of things that these two in some ways might be correlated. Whatever's falling into that error term, those are unobserved, basically start to cause, or not cause, it basically makes it where we can't isolate the effect of X on Y. Because there's something in the error term that's always being in a relationship with X that's also determining Y. Okay, so like I said here, basically on this estimate of unknown parameters, beta naught and beta 1, when I'm trying to speak about the population parameters, I'm going to always try to do it without hat. If you see me mess up on that, I can adjust the slides, just let me know. It's just bad notation sometime on my part. We're talking about the estimators. We're going to be putting a hat on the betas, or the coefficients in this case, to show that this is what it's been estimated. When it comes to the workflow, we have our data, estimations in terms of our minimization problem. We get our estimators, and then we hopefully can start to look at inference. You know, given whatever impact that we see on a particular, the effect on X on Y, we're hoping that in some ways, given all the things we're going to kind of do in terms of trying to correct this or mitigate the problems that we face, that the outcome will be the truth. But I just want to be very careful. And when you're discussing your results, you need to be careful on how you're actually speaking about this. Sometimes you see it in the literature that basically we're just saying, you know, we've done something like an instrumental variable model, and now the bias is gone. No. Basically, you can show that any type of finite sample instruments will cause bias. It might mitigate the problem that you had before, but they're still there. So how you speak about it should be a little bit more careful, that basically you're trying to mitigate the problem, reduce it if all your assumptions are correct. It's not something that I do this method and everything's gone, that my problems are out, they're no longer a problem. It's I've seen it a lot of times when I'm reading articles or reviewing articles. Basically, they're saying that they used IV and the problem's gone. It's not something that simple. And one of the things that I want to show you on what day are we doing that? Wednesday, Friday. It's basically that I can have something that's going to be, suppose my method and everything should be right. I have some of the right properties that I need, but I can show you that the coefficient actually explodes in the wrong direction. So there's a lot of things that can go wrong with certain methods that we're going to kind of look at later on. So just keep that in mind, that basically we'll never know for sure this model. Because of that, we'll never be able to say 100% accuracy this is the case. Any type of test, any types of things that we're doing in that way, or either they're trying to mitigate, but there's always some, there are only a certain probability that they're correct. There's also a chance they're wrong. So always keep that in mind. We're always in an unsure world in this case. We can try to do everything that we can to fix it, but at the same time, it's based on our arguments. It's never going to be 100% correct. Okay, so when it comes to the multiple regression, we're still in the same sort of world, in the sense that we still specify our model. I'm just changing the notation a little bit just for shorthand in terms of matrix. But basically we have our vector predictors here. And always remember that we have a constant as our the first column. And then we have our vector of coefficients. Basically, in terms of dimensions, this is an n by k matrix. Beta is a k by 1 vector, and the product results in an n by 1 vector. So, but even with all that, we still are looking similar to what we were looking at before. Covariance of x and y over the variance of x. And then we can actually put it into a matrix notation again. But the point is that's basically, even and we have multiple regression analysis, we're still focused on this. The problem comes in is that once we have more and more things within this matrix, there's sort of a breakdown in the derivation of this. So this is still true, but we can actually, apparently I didn't put it in there. I might put it in, I guess I'll talk about it later in terms of the bias, but basically for now we'll think about it as just being the covariance of xy over the variance of x. We'll talk about the bias that's sort of introduced a little bit later. Okay, so if we were going to do just our standard wage regression, I probably should have put up the equation, but the wage equation basically has wage on the left-hand side or log wages on the left-hand side, and controls that are on the right-hand side that determine wage. In this case, we always like to focus on education, experience. We could throw a few things in there in terms of experience squared, age, gender. There's a few other things, but for a simple example right now, basically if we're having it in levels, we're looking at the overall outcome of education experience with respect to wage. And if we do it in terms of log wage, just a change in the from level to log level. Basically, when we do this, we are changing sort of the interpretation of that relationship. We need to make sure that we kind of keep track of that as well. In this case, we're thinking about a 1 unit change in education. In this case, I didn't group them together, so basically it'd be a 1 level, going from matric to 1 year of college. Then basically that should increase our outcome by a 1 unit change. That would change our change in wage by 0.64 or 64 cents. It's in US dollars, sorry. But then when we think about it in terms of the log level, we're actually have to think about this as a 1 level increase, and this is actually increasing my wages by 9% in this case. Okay, so it's a difference in interpretation that's in. You can try to go back and forth between the notation, but you need to be, when I say notation, sorry, comparing these across. You can try this. There are some techniques for doing this. But one thing you need to keep in mind is that when we're doing this, there's no direct comparison because of Jensen's inequality. Basically, the expectation of log does not equal the log of the expectation. Okay, so your methods, there have been some, like I said, techniques that are created to sort of do a comparison across. But just make sure that you have that interpretation. Most people are generally okay with this in terms of how they interpret it. So that's fine. Later on, we can show that there are a little more nuances here. One thing that I'm not showing here, but is kind of important, is, basically you're not familiar with the data set yet. So it's called Miraz 1987. In this, they're actually looking at women and working, okay? So if you're not working, you have no wages. So this is one of those things that I was talking about before of throwing things out. Everybody who had 0 wages in this case is gone. If you really want to know how education is affecting your wages, should you be throwing out the people that aren't working even though they're high education? There might be some other influences in there. You're throwing about, I think it's roughly 190 to 200 observations out of the data set. Given there's only 526, that's quite a lot. There are methods for dealing with those zeros. But I'm trying to give you a point that, one, how you interpret it is based on your choice. Also, who you throw out is based on your choice. Which, the thing is that choice is also causing issues with what we're going to refer to later on for bias and how we're looking at these things. You have to be careful. You have to motivate everything that you're doing in terms of why you did that. Even in the case where people basically use the log wage, but then they just add 1 to wage, that's not proper really either. We do it. I see it in research all the time. But if you want it to be very particular on this, you can actually find the minimized constant that is that minimizes the function. You can find the best constant for it. Generally, is not 1. Okay, it's just a trick that we used to use to get to allow us to keep the zeros. Okay, all those things are basically your choices. Is changing interpretations, changing what might be affected in terms of bias. So basically, you're the cause of your own problems. Or us econometricians are, because we don't know the true model. That's the problem. We have complications because our data is observational. All these things are issues that basically we try to overcome and try to explain, and that's what I'm trying to. I know it sound like a broken record. I'm just trying to make sure that your explanation of what you're doing creates. I don't want to say it creates less doubt, but at least the reader doesn't have to guess what you're trying to do. So always be clear on why you did this with the data, why you chose this functional form, why are you logging if you have zeros. All these things are very important to the understanding and the final way that whoever's reading is going to accept it or not. Okay? So even though it seems like a simple example, I've already pointed out like 3 problems that we would need to deal with that I would need to tell someone I did it. Without that, it's just me saying accept what I did and live with it. It's not the way most people that are reviewing your stuff doesn't like that. They like you to be very explicit on what you're doing, why you're doing it. Is there any better methods? Are there problems with you doing it that way? The more you do that, the more they have a good grounding on that you know what you're doing. Or maybe they might not like what you're doing, but at least you're giving them the reasons why. And then they can tell you whether you're wrong or not. Okay? Like I said, it seems like a simple example, but there's a lot of things going on there that I need to explain to you that I left off. So then now I explain them to you. Okay? So that's sort of the setup of just refresher on how we do OLS. And then just pushing you a little further in terms of making sure that you're grounded and, explaining what you're actually doing with the research and, the methods that you're using and the things that are going wrong. Maybe you would watch how you're doing the functional form. When it comes to categorical variables, though, we can see some people in research kind of get maybe a little confused on what's going on with categorical variables just because if it's on the left-hand side, it changes the interpretation of the model. It changes you to something that we see as probability. Okay? Not as the elasticity or semi-elasticity or level models that we had before. Okay? When it's on the right-hand side, a lot of times we see them as measures or qualities that we can attach or that our units of analysis don't have, or they do have. But when you're doing this, you have to make sure that you're interpreting it the right way and you're using it the right way. Okay, so I before used education for that example. Now, a lot of research, we consider that as being continuous. But have you ever seen a measure of education that is continuous? We don't have a thing that somebody finished 11.5 years of school. It's discrete, right? But we treat it as continuous, and OLS will treat it as continuous as well. Okay? I'm not going to say that you should stop doing that. It's just saying that, you need to think about how the measure is. So a lot of times, instead of using every single year of education, we'll group them together. If you've finished less than matric, that's one. You've finished matric, that's another grouping. College, say 4 years, here 3 years, sorry. For undergrad, that'd be another grouping. Instead of having but then once you do that, you're more in the categorical world, not in the odd continuous world that we were doing every grade. So that's why a lot of times people just take it as is and they just don't really explain that. You need to explain that to the reader as you're going through to make sure that they have a clear understanding of what you're doing. So that's why we sort of in this section sort of focus on that qualitative measure. That's how we'll sort of describe this. And when we're thinking about the independent variables, we're just thinking about a binary that's 0 or 1, or a categorical variable that has multiple. And we're always going to be focused on whatever the multiple categories are, we have n-1 new binary variables. We'll kind of get into the reason of that in a minute. When it comes to the dependent variable, we're going to be, I put more later here, but we're going to be thinking about the model as a probability. We're going to kind of point out a few problems that we have with this model. But the reason why I want to point it out here is that there's this push to actually not use it as much in terms of the linear probability model because, you know, probability is not linear a lot of times. But the reason I want to kind of point it out to you is that if you only care about the average outcome, then the answer that you get from the linear probability model is going to be the same, or it should be very close to what you get in terms of the more advanced nonlinear models like Logit or Probit. So a lot of times, I just want you to be clear that, you know, there's a pessimistic sort of way of looking at it and an optimistic way. Just make sure, again, it's one of those things where you at least go through and explain what you're doing, why you're doing it. And if you're only focused on the average outcome, then most likely you're going to be very close to, and the models are typically a little bit easier to use for certain complications that you have as well. Okay? I'm not trying to push the LPM model on you. It's just basically saying that there's some some people view it very poorly, but at the same time, if it's about speed, about being able to use some methods that deal with the unobserved effects, it's available to be used to properly, and then you can check it if you want to against a more complicated model. Okay, so as independent variables, so for now we're just going to focus on the independent variables. We think about these as controls for characteristics of individuals, firms, areas, et cetera, whatever you're thinking about in terms of unit analysis. We want to be able to control for things that we can observe. We can observe gender, we can observe race. Most time we can't observe exactly education, but if you're attending college, most likely, that means you did finish matric, you know, things like that. But so we can mark it as you have the characteristic or you don't. And then most time we can figure out, you know, if you have children or not. We can also subdivide this into number of children and so forth. In terms of industries, you saw me earlier do manufacturing, agricultural, whatever. Foreign firms versus domestic firms. Locations, you know, do you want to be located, you know, in the middle of nowhere or say in an industrial area or something like that? These are all qualities, either you have it or you don't. And in that case, we can then try to figure out, once we do the estimation, how much does this quality increase or decrease the overall effect that we had on our dependent variable. Sometimes that's good. Sometimes we don't really care about the actual quality. You know, it's a control. Sometimes we think of it, some people are overly, well, I'm not going to say overly, they focus a lot on the controls even though they might not be significant, and they're trying to push for those to be significant. The thing is, as long as it has the right sign and certain similar magnitudes, a control should just be a control. If it's not the variable of interest, you know, you can focus on it if you want, but at the same time, as long as the only thing, if it's not significant, that's not always a killer on what you're actually doing. Basically, you can use it, but you're always focused on your variable of interest. As long as it's not one of those, then basically maybe you should just leave it. As long as it's working as what it's supposed to, is controlling for whatever's entering into the error term. Because if you remove it, whatever that quality was might end up in the error term and cause more issues. Okay? When it comes to two categories, like developed and developing, that's where we're creating one new binary variable. 1 if developed, 0 otherwise. Okay? If you only consider these being two types of outcomes, then basically you're putting developed against developing and you're done. Okay. But if you're more in, say, what the World Bank does in terms of they have low income, low middle, high middle, and high income, then if you mark the high income, that's one new dummy variable, versus if you push it against all others, you're comparing the high income against all the others. That means you're not differentiating very well. Okay? So in that case, when you have more than two categories, so n greater than or equal to 3, then basically we need to create a variable. In this case, the example is manufacturing, service, and agriculture. We need to create one variable that's 1 if manufacturing sector, 0 otherwise. Create a variable that is 1 if service sector, 0 otherwise. And that forces the reference group to be agricultural sector, the emitted category. So anything that comes out of these new binary variables is always going to be in relationship to the agricultural sector. So that's the thing about it. We always have to have a reference group to know what's going on in terms of its changes from that reference category. Without that reference category, we'd be in trouble. Okay? So, because if we just say something's high, low, without actually giving a point of reference, it's meaningless. You know, if I say the grades in the course were low to what? Oh, okay, I'll make it up. We're high relative to what? So the thing is, so always make sure that you keep one of these reference categories. Usually we would focus on one that we have a good comparison with. In this case, if you're thinking about agricultural sector, if it's on the decline for most countries because they're becoming more focused on manufacturing or services, it might be a good reference category for that movement. Okay. If we decide not to have a reference category and actually put all 3 in, we could remove the constant, but that turns into a whole other mess. Okay. So for now, just make sure we usually say if you push all 3 categories as one binary variable for each, then we run into something called the dummy variable trap. But just keep in mind that most statistical programs or programs we have here would most likely throw out that additional category because it likes to force in the constant. Okay, so it will sometimes help you, the program itself, but it's better if you keep track of it yourself. Okay, so just think any amount of categories that we have, n minus 1 new binary indicators when n is the number of total categories. This can be quite a large, and we're going to show that on Thursday, in the sense that we can have something referred to as the least squares dummy variable model. And basically we can control for unobserved heterogeneity using it. Okay? So, but in this case, for now, just keep it in mind that however many categories we're looking at, we just want to be able to create n minus 1 new categories. Just to give you an example from what we're thinking about in terms of the education or the wage equation with the left-hand side in levels, education like we had before, and then looking at whether the individual is female or not. Okay? Basically, when we run a model like this, what is going on with the dummy variable here in terms of female is basically causing a comparison with the omitted group, in this case, male. And what we're getting here is a vertical shift of the intercept. Basically what it's telling us is whether this is positive or negative tells us whether it's going to be increased or decreased relative to the constant. In this case, if we're looking at it in terms of equation, basically we have an expectation in terms of female outcome in terms of education, and we have the average outcome in terms of males and education. That's basically what, sorry. Yeah, okay. In terms of beta 1, in terms of these 2 outcomes. So we usually expect the expectation of the error term given, or basically this is telling us there's strict exogeneity. There's nothing that we're not controlling for. Remember, this is just an example. We know there's more affecting wages than in terms of these just two simple variables. But in terms of the, sorry, I need to check this whenever we're on break. In terms of the intercepts, basically we're looking at females is telling us basically it's beta naught plus beta 2. So if you're female, when we're looking at the intercepts of the equation, we see that the outcome is beta naught plus beta 2. For males, it is just beta naughts. So what it's telling us is once we have this outcome for males, is the impact of being female, does it decrease or increase the effect on wages? So if we were to actually graph this out in terms of the predictions, we could see that, well, if I made it a little bit bigger, this is what we get in terms of the constant. So this is what we get for males. And like I said before, once we include the dummy variable for females, what we're doing is we're basically pushing down parallel shift of that outcome. So this is the difference at each education level in terms of wages. Okay, we have difference in basically more females are going into university, more into workplaces, but we wouldn't expect it to be exactly the same. We might actually see that maybe this would narrow if we were to model it with outcomes that allowed for nonlinearities. So this is meant to be just a simple difference. So even if I was to model something with trade and I looked at development or developed versus developing countries, grouping such heterogeneous type countries together, it's most likely not, it'll be an average parallel or difference across. But we're not expecting, say, countries that are at the lowest end of the income distribution to be exactly like what we figure those would be very close to being almost developed. So that's right now it's just being used as a control to show the absolute difference. But at the same time, if we really want to take it into more realistic outcomes, we need to allow for that variation across different types of developing countries. Especially, there's a whole class of new types of research that actually categorize where developing countries are at on their industrialization. That would allow for variation to be across that entire set to show a little bit more variation. Because, like I said, it's unlikely that we would see the exact same here, the exact same somewhere here with matric, and then also PhD and so forth. We would expect there to be some differences. But at the very beginning, we know that this is just meant to be a control. Once we actually start caring about it, we need to be we need to model a little bit more properly after that.